Here's a comparator with a configurable threshold voltage and a positive feedback resistor R3 connected between the output and the non-inverting input of the op-amp. And the question is, how does this circuit work? What happens to the threshold voltage as the output changes? To analyze this circuit, we're going to make a couple of simplifying assumptions. I'm going to assume that R1 is the same as R2. In other words, R2 is the same as R1. I don't care what value they are yet, just that they're the same. I'm also going to do the analysis in two parts. I'm going to look first at the case where the output is low, where V out is equal to VSS, and then when we've done that analysis, we'll come back and say, well, what happens when the output is high, when it's equal to VDD? And I'm going to draw equivalent circuits to help me with my analysis. So I'll redraw the circuit here. We've got VDD and R1. We've got the voltage we're trying to find, VTHR. We've got R2, which is, remember, the same as R1. And we've also got a parallel connection through R3 to V out, which is at the moment equal to VSS, like that. So we can analyze this circuit. It's going to help an awful lot if we combine R1 and R3 in parallel. Now we've got VDD, R1, the middle voltage is VTHR, and our bottom voltage is VSS. So without R3, the threshold voltage would be equidistant between VDD and VSS, and if we slip in one more assumption, I'll assume the magnitudes of VDD and VSS are equal, then VTHR would be 0 volts, but when we add R3, we're making this bottom resistance smaller, because whenever you add resistors in parallel, the total resistance gets smaller, and so here we have a smaller resistance than R1, which means VTHR is going to be less than 0. Let's have a look at the case now where the output is VDD. Again, I'll draw an equivalent circuit. I've got VDD through R1. I've got what was R2, but I'll assume is equal to R1. I've got the threshold voltage, I've got VSS, and now R3 is a parallel connection to VDD. Again, I'll assume that VDD and VDS have the same magnitude. So we've got R1 and R3 in parallel, which means that together they are smaller than R1 on its own. Our threshold voltage will be VDD minus VSS times a resistance which is more than half of R1 plus R1 parallel R3, and then of course we add the VSS term at the end. The point of all of this is that our threshold voltage VTHR is going to come out to be larger than 0. It's going to be a positive number. So we know how to analyze a comparator with a customizable threshold voltage. What is interesting is that that threshold voltage is changing depending on the sign of the output, and since the output is going to depend on the sign of the input. We're going to see VTHR depends on that input. So we can have a look at an input. Here's one I prepared earlier, and I'll draw in the various values I got for VTHR there and there. Remember, we said that VTHR was less than 0 when the output was equal to VSS. So this is VTHR when Vout equals VSS, and the top one is VTHR when the output is equal to VDD. Now let's go ahead and see if we can plot that output. So remember, it's an inverting comparator. So if we have a positive input voltage, we will get a negative output voltage. Here's a positive input voltage, means I expect a negative output voltage. That output voltage will stay negative until VI, our input, crosses VTHR, which at the moment is this line over here. So at this point, we'll see our output change like that, and our output will become positive, and the output will stay positive until the input again crosses VTHR, but now VTHR, it was down here, now it's moved up there. So whereas we would have shifted then, if the threshold hadn't changed, in actual fact we're going to change there, like that. The benefit of this is if we have an input that is especially noisy, especially around the 0 volt threshold, we tend to ignore all of that noise, and we will only cross once. How much noise can we ignore? Well, it's the equivalent of the difference between the two threshold voltages, VTHR high minus VTHR low.